Hello, this is how to graph rational functions using their properties and characteristics. Let's get started. So first, we're going to look at all the properties and characteristics of rational functions. So we're going to use the discontinuities, x and y intercepts, holes, and behaviors at vertical asymptotes in order to graph the function, and then we'll take a look at their max and min, domain and range, intervals of increase and decrease, and finally their positive and negative intervals. So let's look at an example and analyze the properties and characteristics afterwards. So for example 1, we have x minus 7 over x to the third power minus 7x squared minus 4x plus 28. So in order to graph this, first we need to look at the discontinuities and factor the function. So first discontinuity we're going to look at is a hole. A hole occurs when there's the same factor in the numerator and denominator. And in order to find the same factor, we have to factor the entire function. So on the top, we have x minus 7, which is equal to x minus 7 because that's the lowest form. But on the bottom, the x cubed minus 7x squared minus 4x plus 28, that can factor to x minus 7 and x squared minus 4. And since there is an x minus 7 in both the numerator and denominator, there will be a hole at x minus 7. So you see here, there's a x minus 7 factor in the top and in the bottom. So there will be a hole when x minus 7 is equal to 0. And when x minus 7 is equal to 0, x is equal to 7. So there will be a hole at 7. Afterwards, we can also remove the factor, so the x minus 7, from both the top and bottom. And this simplifies the function a lot. So if we remove it from the top and the bottom, we get 1 over x squared minus 4, which helps us a lot in graphing and helps us in the future because it simplifies the function. So yeah, now x minus 7 over x cubed minus 7x squared minus 4x plus 28 is equal to 1 over x squared minus 4. After finding the holes, and simplifying the fraction, the next step is to find the asymptotes, which the vertical asymptotes, the horizontal asymptotes, and the oblique asymptotes, which are the slant asymptotes. A vertical asymptote is when the denominator of the function is equal to 0. So in this case, the denominator of the simplified function, so we're going to look at the simplified function now, the denominator is x squared minus 4. So x squared minus 4 is equal to 0. X squared is equal to 4. You add 4 to both sides. And then x is equal to positive or negative 2 because both of them squared is equal to 4. So therefore, we know that the vertical asymptotes are when x equals negative 2 and when x is equal to 2. If the degree of the numerator is 1 larger than the degree of the denominator, there is an oblique asymptote. Otherwise, there is a horizontal asymptote. So let's compare the degrees of the numerator and denominator. In the numerator, we have 1, which is equal to 1 to the first power, over x squared minus 4. So if we look at the degrees, 1 is less than 2. So the degree of the denominator is larger. Since the degree of the denominator is larger, there will be a horizontal asymptote at y equals 0. That's the rule. So if the degree of the denominator is larger than the degree of the numerator, there will be a horizontal asymptote at y equals 0. However, if the degrees were equal, the asymptote would be at the ratio of the leading coefficients of the numerator and denominator. And this means if this was a 2 up here, so if they were the same, if the degrees were equal, the asymptote would be at the ratio of the leading coefficients of the numerator and the denominator. After finding the asymptotes, we need to find the x and y intercepts. So the x-intercept is when the numerator is equal to 0. In this case, the numerator is 1, so we have the equation 1 is equal to 0. But 1 can never be equal to 0 because 1 is equal to 1. So what this means is that this function never crosses the x-axis. So this function never touches the x-axis. There is no x-intercept. Now, for the y-intercept is the ratio of the constant terms of the numerator and denominator. So in this case, the numerator again is 1, and the denominator, the constant term, is minus 4, which is negative 4. So the ratio would be 1 over negative 4. And therefore, the y-intercept is at y equals negative 1 over 4. All right. With what we know so far, we can plot down a few points and asymptotes on the graph. So this is what we have so far. The red dotted lines are the vertical asymptotes, as we found earlier. They're at x equals negative 2 and x equals 2. We have the blue dotted line, so over here, which is the horizontal asymptote. And then we have the green dot, which is the y-intercept. Remember, there's no x-intercept because it never crosses the x-axis. And finally, we have a hollowed out circle here because I plotted the hole just so that we don't forget later on. So the hole is at x equals 7. So the hole would be here. So yeah, this is what we have so far. However, our graph is looking a little empty, so let's find some more information so that we can draw the entire graph. Alright, next we can find the end behaviors to better understand how our graph will look. So the end behaviors are as x approaches negative infinity and as x approaches positive infinity. So the first one, as x approaches negative infinity, y approaches 0 from above. Now how do we know this? Well, we can plug in a really negative number into the equation to check what result we get. So as x approaches negative infinity, so we can plug in negative 1000 into x, and if we plug it in, we get 1 over 999,996, which is a really small but positive number. So really small means y is approaching 0, but since it's positive, it means it's approaching 0 from above. And as x approaches positive infinity, y approaches 0 from above too. Now, to check this, we can plug in a really positive number, such as 1000, into the equation, and we get 1000 squared minus 4. And this gets us a really small but positive number too. So we get the same answer. So it's really small, so it's approaching 0, but it's positive, so it's approaching 0 from above. So these are our two end behaviors. As x is approaching negative infinity, y is approaching 0 from above. And as x is approaching positive infinity, y is approaching 0 from above. Next, we can find behaviors at the vertical asymptotes. So first we'll look at behavior at x equals negative 2, the negative 2 asymptote. As x approaches negative 2 from the left, y approaches positive infinity. And you'll notice that we always plug in numbers to check. So in this case, as it approaches from the left, so we need a small number directly to the left of negative 2, which is negative 2.001. We plug this in, we get 1 over 0.004001. So since the very small decimal on the denominator, this gets us a really big number that's also positive. So we know that y is going up and it's positive, it's going up to infinity, and since it's positive, it's going to positive infinity. So y is going to positive infinity. Secondly, we can check x approaching negative 2 from the right. And in this case, y is approaching negative infinity. And how do we know? Again, we can plug in a number that's really small and directly to the right of negative 2. So we can plug in negative 1.999 to check. And when we do so, we get 1 over negative 0.003999. This gets us a really big number, so we know that y is approaching infinity. But at the same time, it's negative. So since it's negative, y is approaching negative infinity. And now we can look at the behavior at x equals 2. So as x approaches 2 from the left, y approaches negative infinity. So how do we know this? Well, we can plug in 1.999 to check because it's directly to the left of 2. So when we plug this in, we get 1 over negative 0.003999, which gets us a really big but negative number. So it's y approaching negative infinity. And we can do the same thing for x approaching 2 from the right. And in this case, y is approaching positive infinity because if we plug in 2.001 to check, we get 1 over 0.004001, which gets us a really big positive number. So really big positive means it's approaching infinity from, it's going to positive infinity. And after all those asymptotes, we can finally draw the graph. So again, the end behaviors. So as x approaches negative infinity, y approaches 0 from above. And as x approaches positive infinity, y approaches 0 from above. And then we also drew in the behaviors at the asymptotes. And notice I also made sure to include the whole here because it never actually touches when x is equal to 7. There's no point at x equals equal to 7. So yeah, this is what our graph looks like now. Let's take a look at a few more characteristics of this graph. So we can find the local max of this reciprocal function. This function only has a local max and no local min. If you look, there's only one point here, that's the local max. And to find the local max, we can use the original function. So, I drew in the original function over here in purple. The original function is y equals x squared minus 4. So the reciprocal function is 1 over x squared minus 4. The original function is y equals x squared minus 4. So that's the original function. The x value will be the same. So the local max, you see they both have the same x value. They're both at x equals 0. And the y value of the local max on the green graph, so of the reciprocal function, is the reciprocal of the y value of the absolute min of the original function. So if you look at the purple graph here, the absolute lowest point is at 0 and negative 4. So the y value is negative 4, right? The y value is negative 4. The absolute min value is negative 4. And so the local max of the reciprocal function is the reciprocal of negative 4, which is negative 1 over 4, negative a quarter. So you can see here, this point, this green point here is at negative a quarter. All right, let's take a look at domain and range. So since there is one hole in our graph, we will need to take that along with our vertical asymptotes into account when stating domain. So our domain is x belongs to R, so x belongs to all real numbers, where x is not equal to negative 2, because that's our first asymptote, along with x is not equal to 2, because that's our second asymptote, and x is not equal to 7, because that's where our hole is. All right? Now for the range, we need to take a look at our local max and mins. The range has to be above the local min and below the local max. So what we have here is f of x belongs to R, where f of x is greater than 0, but at the same time, f of x belongs to R, but f of x is less than or equal to negative 1/2. So that's what we have here. But at the same time, for the range, we need to remember the hole at x equals 7. If we plug in 7 as x into the equation, so into here, 7 squared minus 4, we get y equals 1 over 45, which is another value that is not in the range because of the hole. So here we have f of x belongs to R, where f of x is not equal to 1 over 45. So these three are our range. Now we can try to find the intervals of increase and decrease by looking at the graph using local max and min and using the original function. So f of x increase. When we look at the graph here, f of x is increasing, as in the y value is constantly growing from negative infinity to negative 2, as you can see here, and from negative 2 to 0. So it changes at 0, so everything starts decreasing, but from negative infinity to negative 2, and from negative 2 to 0, it's constantly increasing. The reason why I use circle brackets here and a union is because since there's no actual value at x equals 2, so since there's an asymptote here, there can't be anything at negative 2. So that's why there's circle brackets here. So it's from negative infinity to negative 2, and from negative 2 to 0. The same thing happens on the f of x decrease. So f of x decrease is when from 0 to 2, so from 0 to 2, the asymptote, from 0 to 2, from 2 to 7, so from 2 to 7, again, circle brackets because there's nothing actually at 7, because the whole is at 7, right? The whole for x is at 7. So from 2 to 7, and then from 7 to positive infinity. So from 0 to 2, from 2 to 7, and from 7 to positive infinity, it is constantly decreasing. One cool thing to remember is that when a function is increasing, the reciprocal function is decreasing, and vice versa. So for example, if you see here, in the original purple function, it is decreasing all the way until 0. And so the f of x the reciprocal function, so the original function is decreasing until 0. So the reciprocal function is constantly increasing until 0. And then when the original function starts increasing, the reciprocal function starts decreasing. So that's cool to remember. We can also find positive and negative intervals by looking at the graph and using an interval chart. So by just looking at the graph, we can tell that f of x is positive, so it's when it's greater than 0, when it's from negative infinity, so from here, until negative 2, from 2 until 7, and from 7 until positive infinity. Again, we're using the circle brackets because it doesn't include the asymptotes, and it doesn't include the whole. So all of this is above 0, it's positive. So from negative infinity to negative 2, f of x is positive. From 2 to 7, and from 7 to positive infinity, f of x is positive. And when is f of x negative? Well, f of x is negative from negative 2 to 2. And circle brackets again because the asymptotes are not included. So negative 2 to 2 is when it is negative. Now, how do we find this using an interval chart? So using an interval chart, our only factor in the denominator here is x squared minus 4. So we put x squared minus 4 here. And then we have our intervals up here. So from negative infinity, we have until negative 2, until 2, until 7, and until positive infinity. So we plug in values from the range here and see if we get a positive or negative value. So let's say we plug in a really negative number, right? Let's say like negative 1,000. When we square it, we get a really big positive number. So when we minus 4, the 4 doesn't matter that much. It's positive anyways. So no matter what we get, we always get positive. Now let's say from negative 2 until 2. So let's choose a random number in there. Let's say we choose 1. If we get 1 squared, we get 1 minus 4. That's negative 3. So we get a negative interval between negative 2 and 2. And then we do the same for the next two intervals. So we can choose any number between 2 and 7, plug it in, and it'll give us a positive value. And then any number between 7 and positive infinity, we can plug it in, and it'll give us a positive number too. And just like the last one cool fact to remember is that a function and its reciprocal function are positive and negative at the same intervals. So if you notice here, this part's positive, right? All before x is equal to negative 2, the purple and the green graph are both positive. Between x is equal to negative 2 and x is equal to 2, we have both of them are negative. And then from x is equal to 2 to x to positive infinity, both of them are positive again. So yeah, a function and its reciprocal are positive and negative on the same intervals. Now let's look at a second example that's similar, so we'll use the same steps, but it has a few different characteristics that we can analyze. And our example will be x over x squared minus 2x minus 3. So again, first we need to determine the discontinuities. So we'll start with the whole again. A whole occurs when there's the same factor in the numerator and denominator. So let's factor it again. If we factor it, we notice that it becomes x over x plus 1, x minus 3. And so in this case, there is no common factor in the numerator and denominator. And so there is no whole in this graph. There could be asymptotes, but there are no wholes. And we cannot simplify the function any further, so this is the simplest form, since there are no common factors that can be removed further than this. Now let's try to find the asymptotes again. So the vertical asymptote, the horizontal asymptote, and the oblique asymptote, the slant one. Again, the vertical asymptote is when the denominator equals 0. So if we see here, x plus 1, x minus 3 is equal to 0. So x is either negative 1 or positive 3. So as we see here, the vertical asymptotes are when x equals negative 1 and x equals 3. And again, if the degree of the numerator is 1 larger than the degree of the denominator, there is an oblique asymptote. Otherwise, there is a horizontal asymptote. So if we see here that the degree of the denominator is larger, since it's 2, and the degree of the numerator is only 1. Therefore, the horizontal asymptote is again at y equals 0. However, if the degrees were equal, so if this was also a squared here, if this was also a 2, the asymptote would be at the ratio of the leading coefficients of the numerator and denominator. So if this function was like 3x squared over 4x squared minus 2x minus 3, then the degrees would be equal. And so the asymptote would be at the ratio of the leading coefficients, which is 3/4 in the example that I just gave. The next step again is to find the x and y intercepts. So the x-intercept is when the numerator is equal to 0. So in this case, the numerator is just x, so x is equal to 0 when x is equal to 0. So therefore, the x-intercept is at x equals 0. It intercepts at x equals 0. Now, the y-intercept is the ratio of the constant terms of the numerator and denominator. So in this case, we can just add a plus 0 to the end since it doesn't actually change the numerator. So if we add the plus 0, we'll say the numerator constant term is 0, and the denominator's constant term is -3. So 0 over -3, that just becomes 0. So therefore, the y-intercept is at y equals 0. And you'll notice that since x equals 0 and y equals 0, it intersects the origin. It passes through the origin. This function passes through the origin. And we can see that on this graph where we plotted down the vertical asymptotes and the blue dotted horizontal asymptote. So again, we have the x equals -1 and the x equals 3 vertical asymptotes here. We have the blue horizontal y equals 0 asymptote, and the green dot is the x and y int, which is 0, 0, so the origin. Next, we can find the end behaviors to better understand how our graph will look. So again, as x approaches -infinity, y approaches 0 from below, and we can check this by plugging in a really negative number to check. So, for example, -1000. So -1000 over -1000 plus 1, -1000 minus 3, which is -1000 over 1,001,997. And this gets us a really small number that's also negative. So really small means it's approaching 0, and negative means from below. So it's approaching 0 from below. As x approaches positive infinity, y approaches 0 from above. And we can check this by plugging in a positive number, and you'll see the result is also a very small number, so it's approaching 0, but it's positive, which means it's approaching 0 from above. And we can find the behaviors at the vertical asymptotes as well, starting with behavior at x equals -1. So as x approaches -1 from the left, y approaches -infinity. We can plug in -1.001 to check because it's directly to the left of -1. And this gets us a really big number, which means y is approaching infinity, but it's also negative, which means y is approaching -infinity. Same thing we can do for x approaching -1 from the right. We plug in -0.999 to check because it's directly to the right, and this gets us a really big number, but and it's also positive. So really big means it's going to infinity, and positive, which means it's going to positive infinity. So as x approaches -1 from the right, y approaches positive infinity. And the second asymptote, behavior at x equals 3. So as x approaches 3 from the left, y approaches -infinity, plugging in 2.999 to check. And this gives us a really big number, so infinity, and big negative number, so approaches -infinity. And as x approaches 3 from the right, y approaches positive infinity, and we can check this by plugging in 3.001, which is directly to the right of 3, and this gets us this number, which is really big and also positive. So as x approaches 3 from the right, y approaches positive infinity. And now our graph looks like this. So drawing in the behaviors at the end behaviors, the behaviors at the asymptotes, we get this graph. So we can see that this is also a reciprocal function, but it looks a lot different from our first example. And we can find more of those differences by looking at some more characteristics. Now let's take a look at this graph. The interesting thing is that there is no maximum or minimum value for this graph. As you can notice, there's not a set minimum value or a set positive value, right? So there's no maximum or minimum value. But there are actually specific instances when this can occur. So there's no maximum or minimum value, and this occurs when either one, the value is constant. So when there's a straight line, there's not going to be a minimum or maximum. If the graph is always increasing, or if the graph is always decreasing. So let's take a look at our graph. Over here, it approaches 0. So as it goes, as the x value increases, the y value decreases, and it keeps decreasing. Over here, it keeps on decreasing. And over here, it just keeps on decreasing. So, since our graph is constantly decreasing, there is no max or min value for this graph. Now for domain and range. For domain, since there are no holes in this graph, we only need to worry about the asymptotes when trying to find domain. So x is a member of the real numbers, where x is not equal to -1 and x is not equal to 3. So those are where the asymptotes are. For range, we need to take a look at local max or min, and again, the range has to be above the local min and below the local max. But again, since in this case there are no local max or mins, the range will just be all real numbers. So x is an element of the real numbers. It's all real numbers. We can find the intervals of increase and decrease by looking at the graph and using local max and min too. So f of x increase, as I mentioned before, the graph is constantly decreasing. So there is no increase, it never increases. So NA, not applicable, there is no f of x increase. But f of x decreasing, there is. It is constantly decreasing except for at the asymptotes, because there are no actual points on the asymptote. So we have to write it out. So we have here -infinity to -1, circle bracket, so not including the asymptote, -1 to 3, not including the asymptote, and 3 to positive infinity. So that is when f of x is decreasing. And again, the thing to remember is that when a function is increasing, the reciprocal function is decreasing, and vice versa. So if we were to flip this over, if we were to flip this reciprocal function over and get the reciprocal of this function, we would get a function that is constantly increasing. Now let's try to find the positive and negative intervals by looking at the graph and using the interval chart again. So f of x is positive from -1 to 0, so in this interval, the slim interval, and from 3 to positive infinity, this giant interval. And f of x is negative, so below 0, from -infinity to -1, so this interval here, and 0 to 3, so this interval here. And this is proven better by the interval chart. So we have our factors here, x plus 1, x minus 3, and x. And then the last one is the overall positive or negative. These are the intervals, -infinity to -1, -1 to 0, 0 to 3, 3 to positive infinity. And so all we have to do again is to plug in the values. So if we plug in any really negative value, this will be negative, this will be negative, and x itself will be negative. So the overall positive or negative of this interval is negative. From -1 to 0, x plus 1 will be positive, but these two will be negative. But all of that added together, the overall interval will be positive. Same thing with these two intervals. So positive, negative, positive. Overall will be negative. And positive, positive, positive. The overall will be positive. And you can see it goes negative, positive, negative, positive. And in the graph here we have negative, positive, negative, positive. So that matches our graph, which is very good. And again, the one thing to remember is that a function and its reciprocal are positive and negatives at the same intervals. So that is how you are able to graph reciprocal functions using their characteristics and how to analyze them after we graph them. So thank you.